All right, and there is a homework due tonight. I hope you've had a chance to check it out. It's a little bit longer than usual because it covers 3 days worth of stuff because of the test instead of the usual 2. So don't leave it to the last minute. All right, great. Let's. We have, as far as I can tell, 5 more class meetings until the. So there are 6 total, but the last one is going to be our last test. The last day of class will be a test, which in theory you could finish everything by then, but then the final exam will be just sort of you all collecting any questions which remain to be answered. There's no real new material on the final exam. Anybody got any questions about that? I hope everybody knows what's up. All right, excellent. Let's continue then. Oh, I wanted to say just about the homeworks. I hope, thank you all for doing the homeworks. Some people lately have stopped doing the homeworks. I don't know, I'm not sure why, and I haven't been hassling you about it. That's because I don't like to hassle people, but if you have been not doing the homeworks and you haven't heard anything from me about it, that's not because it's okay with me, or maybe it is because it's okay with me. Like, I'm okay with you not doing the homework if you don't do the homework. You're still getting a 0 for those assignments, though. Like, I mean, I don't feel badly deep down inside my heart if you don't do the homework. It is bad for you, though, to not do the homework. So do the homework. I don't know. I mean, it's a free country, right? Yeah, you can just not do it if you want to, but you are forfeiting part of your grade. Okay. Anyway, let's talk about initial value problems. I have a couple more examples of these to do. Initial value problems, and then we'll move on to something new and exciting. The thing we're going to move on to is the thing that I had forgotten to put on the checklist until the latest version. Initial value problems, anyway, this has always been on the list. Initial value problems are like the most, I would say, one of the most common applications of the antiderivative, like in the real world. And I thought maybe we'd do a simple one from physics, and then I've got one for you all to try that's from something else. So initial value problems, remember the idea, maybe I'll do just like a totally abstract one, and then we'll do 2 word problems. So something like, they're always about find a function f of x where I tell you the derivative, f prime of x is, I'm just making this up here, how about 6x plus 7, and also you are told a single initial value, something like that, f prime of 1 equals 8. I don't know how these numbers are going to work out, but hopefully everything will work out great. So this right here is the initial value. And your job is to find the function f of x when I told you the derivative, f prime of x, all right? So basically you are going to do the antiderivative, because in this case I told you the derivative, but you have to figure out what the original function is. The initial value is used to solve for the c. So this is the initial value, and you use this to solve for the plus c part that you always get when you do the antiderivative. I hope everybody remembers. You always get the plus c. And if you're not given the initial value, there is no way to determine what c is. But if you are given some initial value, then you can solve for the c. So this is a fairly simple function here. So first of all, to find the function itself, the original function, you have to do the antiderivative of what we started with, because here I told you the derivative, and I'm asking you for the original function. So you begin by doing the antiderivative. This will generate the plus c, and then you solve for the c by using the initial value. So here, 6x plus 7. Any experts out there? Can you tell me the antiderivative of that? Anyone remember the antiderivative? Yeah?
It would be 3x squared plus 7.
3x squared plus 7. That's great. If you were not simplifying, you could write it this way. 6 times 1/2 x squared. So you just do each part, right? X becomes 1/2 x squared. And then 7, being a constant, becomes that same constant times x. So it's 6 times 1/2 x squared plus 7x. Of course, plus c. I'm pretty sure she said plus c, right? This, of course, is 3x squared plus 7x plus c, right? So that's my f of x. Now, I'm not totally done here because of the plus c. Your job here was just find a function f of x. This is kind of the answer, but we should solve for the c. C is, at this point, an unknown constant, but we can figure out what the c is by using the initial value. Oh, I'm sorry, I've made a horrible error. Can you scribble this out with me? See that prime right there? That should not be a prime. Sorry, this should be just f of 1. The initial value is always given as a value of the function itself, not of the derivative. If I give you a value of the derivative, actually that does not let you solve for the plus c. Sorry about that. Okay, anyway, from here we now use the initial value. So from this point we're going to plug in the initial value. And the initial value, come on now, says f of 1 equals 8. So I'm going to plug in x equal 1 and then set it all equal to 8. That's what f of 1 equals 8. It means when you use 1 for the x value, then the answer is 8. And so I'm going to plug in 1 for the x. So right here, plugging in 1 for x, it says 3 times 1 squared plus 7 times 1 plus c all equals 8. Right? And I think the numbers will work out nicely this time. So just simplify this. I mean, this is easy to do without a calculator. In some cases, you would want to use a calculator in this step. But this just says 3 plus 7 plus c equals 8. That's 10 plus equals 8. Solving for c, c equals -2. I think I got that. All right, and now the work is basically done, although we should say clearly what the answer is. The answer is this. This is my function, only now I know what c is. And so my final answer is, so f of x is 3x squared plus 7x minus 2, like so. That's that. All right, any questions or thoughts about that? Great. So this is kind of an easy sort of abstract example. I had one word problem, like real life problem based in physics, and then I have another applied problem for you all to try, and then we'll go on to something completely different. This initial value problem business was a big deal. I mean, remains a big, like one of the major applications of calculus. So let's do a little physics. Like all of this stuff was really invented in the context of physics and specifically to answer questions like this one that I'm about to say. How about I throw a ball in the air at a speed of, let's say, how about 5 meters per second. I think that that's kind of a slow throw of a ball. I don't know. I'm making this problem up, but that's a reasonable speed at which I could throw a ball. I think 5 meters is that like from here to the door maybe? And I could throw it that far in 1 second, I think. Certainly I could, right? Anyway, maybe that's a slow throw. I don't know. My question is, but I'm throwing it straight up. That's what I said, in the air. This is what I mean. Throwing it straight up. And my question is, at what time does it reach its highest point? This is a very basic kind of simple physics problem that I bet you can imagine has a lot of real-world utility applications. People were using calculus in the very early days to answer questions about like ballistics and artillery firing. If I shoot a thing at a certain angle, how far is it going to go? When does it reach the top of its arc? And then when does it hit the ground again? All of these are questions which you can answer using simple initial value problems. So there is one little piece of information that you need to know about physics of falling objects, and that is the strength of gravity. This depends on the strength of gravity. Obviously, like the answer to this question is different. If I was on the moon or something and I throw a ball up in the air, it will go up for a lot longer than on the Earth. So we have to use the fact that on the Earth, the acceleration experienced by gravity, anybody happen to know there's a constant value of the acceleration due to Earth's gravity if you're on the surface of the Earth? The answer is negative 9.8 meters per second squared. This is a weird unit, but what that means, this is acceleration, so it tells you how fast things gain speed, right? That's what acceleration means. And it says in every second, a falling object gains 9.8 meters per second worth of speed. The negative there is meaning down, like things due to Earth's gravity fall downwards rather than up, of course, and that's why it's usually written with a negative sign. So negative indicates down. All right. Anyway, this is the acceleration due to gravity on the surface of the Earth. This is a little different if you are closer to the center of the Earth than we are right now, but anyway, that's that. Let's try and work this out. So the other basic fact, which is not really a physics fact, but just a basic fact that you need to know in order to solve a problem like this, is that the acceleration, so here's another simple fact that we have talked about before. Acceleration is the derivative of velocity, right? How fast the velocity is changing, that's the same as acceleration. Another way of saying that is the velocity, if I write it in terms of functions, the velocity is the antiderivative of the acceleration, all right? And actually that's a more useful way in a problem like this. Because in this problem, we know what the acceleration is. It's this negative 9.8. The acceleration is just a constant value. And so we can figure out what velocity is by doing the antiderivative of the acceleration. And then the initial value has to do with how fast I'm throwing the ball into the air at. But anyway, let's find, so using this, we can find a formula for v of t, right? Because it is the antiderivative of the acceleration. So I can go v of t is integral of a of t, but dt, but the a of t is just that number, negative 9.8 dt. And this is a very easy antiderivative. It's just a constant, and so our answer is just that constant times x, or in this case it's t because I'm calling the variable t. So the antiderivative is just negative 9.8 t plus c. I put the t there because this is the integral of a constant, is that same constant times the variable, which is usually x, but in this case it's t. And then, as always, you put the plus c, all right? Okay, this is a formula for the velocity. Can we solve for the c using the initial value? Now, up here, if you look at that other piece of information I gave you, which was the initial speed, the speed of the ball, all right? The speed of 5 meters per second. You need to translate this into a formula. Usually how I would write it would be something like this. V of 0 equals 5. That means at time 0, the velocity was 5. I throw it, and it's positive 5, meaning 5 up. I throw the thing up at a speed of 5 meters per second. All right? And so we can easily plug that in over here. So we plug, what that means is we plug in t equals 0 and set it equal to 5, just like we did before. And we should be able to solve for the c. This will be actually very easy to solve for the c. It'll say negative 9.8 times 0 plus c equals 5. And of course, times 0 on the left side is just 0. So that just says c equals 5. And so my formula for the velocity is negative 9.8 t plus 5. All right. Excellent. All right, so we have determined the speed of the ball at all times. If you want to know the speed after 3 seconds or whatever, you would plug in t equals 3. Yeah?
Why don't you plug in the t for 0 in that one?
The t for 0.
Like, why isn't it like the final form? Oh, wait.
I think that's what I did.
Oh, wait, never mind, you did. Oh, never mind. I was thinking of the formula. Never mind.
Yeah, it's because the c happened to equal 5, and so then I
Yeah, okay.
replaced the c by 5. Yeah, it's a little confusing. There's not a lot of work you have to do to solve for the c in this case. All right, can we answer the original question that I asked, which was not exactly that? I mean, we found now a formula for the velocity at all times. The original question I asked, at what time does it reach its highest point? We can rephrase this in terms of velocity. I believe if I throw the ball up, the highest point in terms of velocity, the highest point is reached when the velocity is 0, right? That's the point. The ball goes up, its speed is sort of upwards for a while, but then of course it comes back down after a while. At that point its velocity goes negative because it's going down. But there will be one moment when the velocity equals 0, and that will be the highest point of the arc of the ball. So the highest point, I will say, highest point is when velocity is 0. And so we can set that thing equal to 0 and solve for t. This is, again, easy to solve for t. You subtract the 5 and then divide by 9.8. Negative 9.8t equals negative 5. And here I will, this is about a half, but I'll do this on my, no, about 2. No, about a half. I got it backwards. I am doing this on my calculator. 5 divided by 9.8, sorry. 0.51 seconds. This is the answer, right? Sorry, I'm off the bottom. This is the time at which the ball reaches its highest point. All right. This is a made-up example, but I hope you can imagine that this was kind of a big deal when people originally figured out how to do this. Like before calculus, this was essentially not known how you could answer questions like this. Now this one, in a situation with constant acceleration, it's a little bit easier. So you probably, I imagine people could have done this before using calculus. But when the acceleration is changing over time, like for instance, if you have a rocket that's going up, matters are complicated by the fact that the rocket, as it burns its fuel, its mass is changing, and so its acceleration actually changes while it's going up. And this makes things much more complicated from an elementary point of view. But if you know how to do it using calculus, then everything is still easy to do. So that's a sort of very realistic example of what old school calculus was being used for. This is exactly the kind of situation that people sort of, the originators of calculus invented it to solve problems like this. It was a big deal. All right, any thoughts about that? All right, let's get to, I got one for you all to try. So this is a completely different applied scenario, which you don't have to understand anything about it really, but let's try another one here. It's another initial value problem. So let's say we're studying some kind of sample of cancer cells that are growing over time. So I'm going to call that n of t. This is the number of cancer cells in my sample. N itself is like a very big number, right? Because it's a number of cells. And then let's say, and we can measure, I don't know how realistic this is exactly, but this is inspired by a problem I saw in the book, so maybe it's realistic. They tend to do a better job of researching their real world problems. Let's say that we measure n prime of t. So this is a scenario, you have to imagine a situation where you are able to measure the growth of these cells without actually measuring the number of cells. This is, I can imagine that actually if I give you like a petri dish full of cancer cells and I ask you how many cells are in there, this is not a question that's easy to answer. You could, I suppose, count them with a microscope, but you wouldn't ever want to do that. I can imagine there are some situations when it's easier to tell how many cells just appeared in the last minute. That seems to me an easier question to answer than how many total cells are there. So in this example, you know the derivative even though you don't know the original function. All right, and I'm going to say, this is like a part A and a part B. Find n of t, assuming that 300 cells are present on day 0. Let's say the t is in days. All right? Maybe we'll do the part B together. Let's just, I'll have you guys try and do this part A. You should begin by doing the antiderivative of something, right? Here I told you the derivative. Your job is to find the original function here. And then this business is going to tell you about the initial value. See what you think. You may have to remember something about the antiderivative of the e kind of thing. Doing all right? Yes, the rule for the E is number of
Yeah.
I mean, you went every far in the eye.
This.
Just wrote it down. Oh, he's on the outside? Yeah. Oh, the E3.
Yeah,
So it's 60 and
Yeah.
No, it's high.
I thought that you were like,
I don't even look at it. I was like, it seems like they have
Oh, yeah.
All right, shall we discuss this one? It looks like people did pretty well here. So for this one, you should begin by doing integral of 60e to the 3t dt, right? And remember your integral rules for e to the something, something, something. The rule that you should find in your notes somewhere is this. Integral of e to the kt, you probably wrote it using x's, but whatever. E to the kt becomes 1 over k e to the kt plus c, of course. So this, and what do we do? What do we do with the 60? The 60 is just a constant coefficient, and so it remains as a coefficient in front of the answer. So it's just 60, and then I got 1/3 e to the 3t plus c. That's the antiderivative. I hope that's what you settled on. All right, and then I guess you could simplify a little bit here if you want to. N of t, 60 times 1/3 is 20, right? E to the 3t plus c. So this is not my final answer, but that's getting there, right? The final answer is what happens after solving for the c. So now we need to solve for the c. And my initial value, which sometimes I write IVP is sometimes what people write for initial value problem. The initial value, you have to, in this case, kind of interpret the words a little bit. I said, assuming that 300 cells are present on day 0. The way to write that in the formulas would be n of 0 equals 300, right? On time, when the time is 0, the number is 300. And so what we're going to do here is we're going to plug in t equals 0 and set equal to 300, right? And so it says 300 equals 20e to the 3 times 0 plus c. And we can solve this for c because those are all numbers. That e to the 3 times 0 is just e to the 0, which is 1. So this says 20 times 1. So really that's just 300 equals 20 plus c. And then we subtract the 20. C is 280. All right, I hope this is what you all did. And so my true final answer is the number time t is 20 e to the 3t plus 280. This is the solution to the initial value problem. All right, that was the part A. I said let's do the part B together. This you'll see some questions like this on the homework which can be a little bit confusing. So the part A was this. Find a formula for n of t. And then the part B says, find the number of cells on day 10. All right. The part B, given what we've already done, the part B requires almost no work, and it certainly doesn't require any calculus. In the part A, we already found a formula for n of t. For whatever t you want, you can use this formula to find the number of cells on day t. And so, in the part B, find the number of cells on day 10. That just means you use this formula that you already found and plug in t equals 10. So for this one, you just plug you know, it's n of 10 is what I'm talking about, right? So you plug in t equals 10 in the answer for part A. All right, and what is it? It would be n of 10. This is the number of cells on day 10 is 20 times e to the 3 times 10 plus 280. That's e to the power 30, which you can't do, you know, by hand or whatever, but you can put that in a calculator if you want to. It's a very big number. This I plugged into my calculator. This is something like, in the scientific notation, 2.13 times 10 to the 14. So this is a 14-digit number. It's very big because e to some power is very big. All right. Starting with 300 cells, it grows to this many cells after 10 days. I don't know how realistic that is. All right. This is initial value problems. Super useful in the real world, and really one of the original applications of calculus in the old days. All right, great. We got something like 45 minutes left, and I think that's enough time to start the next section. Well, it's certainly enough time to start the next section. And so this is the section that I accidentally left off the checklist earlier in the semester and realized it. That's why I gave you a new one. This is the substitution, sometimes referred to as the u-substitution. And different people have different opinions about this, but I would say, in general, students in this class tend to think that this is the hardest thing on the list. This is one of the harder sort of things that we are going to do during the semester. So get ready for that, I guess. I'm not trying to scare you. I'm trying to inspire you. This is a trick for doing derivatives, and it's a more sophisticated trick. I'll just say this is a somewhat fancy trick. Did I say derivatives? I meant antiderivatives or integrals. This is a fancy trick for doing the integral. We haven't actually talked about any fancy tricks for doing the integral yet. We had very simple tricks, which are things like, if you see a product of two things, you should actually like multiply it out, which sometimes means like do the FOIL or distribute or something like that. We had simple tricks based on distributing. This substitution is actually a more sophisticated trick for doing the integral, and it's based on the chain rule, but trying to do the chain rule backwards. Of course, the chain rule is a rule for the derivative. The antiderivative is about reversing the process. So it's based on doing the chain rule backwards. So maybe I will refresh our memory about what the chain rule says. So the chain rule, if you were to write out the chain rule as a formula, which I actually, in general, I don't suggest memorizing this as a formula, but this is what it is in any case. It's about the derivative of a thing inside of another thing, and the answer is the derivative of the outside with the same thing on the inside times the derivative of the inside. All right, that's the chain rule written out as a formula. Usually we don't write it out as a formula, but that's what it is if you want to write it as a formula. And what that means is, if you write it the other way around, it becomes a formula for the antiderivative. So, as an antiderivative, it means, so this one up here says the derivative of that equals that. The other way around means the antiderivative of the right side equals the left side. So that would say integral f prime of g of x times g prime of x dx equals f of g of x. And then I have to put the plus c just because you always get the plus c when you do the integral of anything. All right, so this is writing the chain rule the other way around as an antiderivative. The antiderivative of the answer equals the thing we started with. All right. And what you see on the left side is this right here is a product. This is a product of two things. which means this formula here can sometimes be used to take the integral of a product of two things. But it only works in the very specific situation when the first thing looks like that f prime of a thing on the inside, and then the second thing looks like the derivative of that inside thing times dx, all right? So this is a product of two things, so this can be used sometimes, and this is really, I think, what makes this a hard technique to use, is because sometimes it just doesn't work at all. And there's not really a rule about when it works and when it doesn't work. You know, for the derivative, you have the product rule, which always works. For the integral, you have this, what we call the substitution trick or whatever, the substitution strategy. And it doesn't always work, and it's not always obvious how it's even supposed to work. But I will say this can be used sometimes to do the antiderivative of a product. Because that thing over there on the left side, it really is a product of two things. It's the f prime of g of x times the g prime of x, with the dx, of course. All right? This can sometimes be used to do the antiderivative of a product. All right? Now, when we actually do this trick, actually it looks quite different. So I'm trying to give you a little bit of the theoretical background, but actually this as a formula, I'm not going to tell you to memorize this as a formula because it's not, it doesn't really work that way. That's not the best strategy to do this. So here's how we're actually going to write this. It will look somewhat different. So we write it like this. We write it like so. In this case, of course, from the chain rule, we always have the outer function and the inner function, right? The outside, throughout this, we're calling the outside f and the inside g. So I'm going to say, let u equal g of x. This is usually called the u-substitution, just because when people do it, they usually use the letter u. I don't know why. You can call it whatever you want, of course, but for some reason, people tend to use u. Let the u be g of x, and let the du be g prime of x times dx. All right? And if you do that, this is actually why it's called the substitution, because it involves looking at a piece of the formula and turning it into u. That's the substitution. If you write it in these terms, then this thing, which you can still see on the top, it takes a simpler form. Then this just says, integral of f prime of u times du, right? This g prime of x dx is what I said we're going to call du. And over here it says f prime, here it says f prime of g of x, but I said g of x was going to be called u. So now it says integral f prime of u du. And then on the right side up here, it would just say f of u plus c, right? You always get the plus c, of course. And this formula actually is kind of self-evident. I mean, if you're wondering, I don't know if you're wondering at this point, is this really going to work or something? It's probably not clear enough in your mind yet. But this just says the antiderivative of the derivative of f is equal to f, which is always true. That's the integral of the derivative equals f. All right. Let's just try an example using this technique. I know what I've said so far doesn't really explain how to do this at all in practice, but I am going to start. This one is sort of an easy example, and then we will make them a little bit harder, little by little. All right, so first of all, you should look at this and realize there is no simple way to do the antiderivative in this example, because I have, first of all, there's a product here, 2x times this thing. And so already you generally can't just do the integral. If you have a product, you cannot just do the antiderivative of each part. Your only hope in, as far as what we've done so far, is to try to multiply it out, try to distribute. But this sixth power messes that up. You can't distribute this under the sixth power. That's just not allowed Really, your only option would be to actually multiply out, like do the FOIL 6 times, which nobody wants to do, and we are not going to do. Instead, you should do the substitution. So when you see something fairly complicated like this, it should occur to you to do the substitution. And we need to, and this is immediately what's difficult about the substitution, you have to choose which part you want to be the u. And it's completely up to you. If you make the wrong choice, it's not going to work. So there's sort of an art and an intuition about general strategies about how you choose the u, which we're going to talk about. But generally, remembering the chain rule, the u refers to the inside part here, right? It's the g of x. So what you want to do is look at this thing, find something which is on the inside of something, and that should be the u. So in this example, the only thing that kind of fits that description is the inside of this parentheses, all right? So we are going to choose u to equal x squared plus 10, all right? And this is sort of unfortunately vague because there is no hard and fast rule about this, but I'm going to say generally choose the u to be, I will say, the inside of something. And what that something could be, it could be just ordinary parentheses like it is in this example, the inside of those parentheses, or it could be the inside of a square root sign, or the inside of an exponent of something. These are things that we're gonna do a lot of different examples, but this is something that you just have to get used to. There is no hard rule about this, and sometimes you have to kind of bend the rules a little bit. But anyway, choose u to be the inside of something, and then we can calculate the du. See right here, when we choose the u to be dx, you make the du equal g prime of x dx. So here we can calculate, we find du is always the derivative of the u. See, u is g of x, du is g prime of x. So the du is the derivative of the u. In this case, it would just be 2x. And this is sort of a technicality. Du always includes the dx. I put it right here. And you should put it here also. All right, so I'm going to continue my commentary here. You choose u to be the inside of something, and then du is the derivative of u. This is not so hard to remember. And I will just say, parenthetically, including the dx. All right, so in this example, du is 2x dx. All right? And now we are going to do the substitution. This is called the substitution because I'm going to plug this stuff into the original formula here. So what I'm going to do is, this guy here, I'm going to say, this is the same as, I don't know about that 2x, but this is just u to the power 6, right? I'm going to try and do this in like little baby steps one at a time. So what I did here was, you just plug in u, sort of where it goes. Remember, when we started the problem, we picked the u, and so you should always know where the u is going to go when you plug it in. All right, it is inside the 6th power. Now there's some other stuff left over, and that stuff I am going to just rewrite things. I'm going to rearrange the ordering just to put that stuff together. U to the 6th, of course, you don't need these parentheses anymore. It's just u to the 6th. I'm going to write that first. And then everything else that's left over is this 2x and the dx here. So I'm going to put those over here. So this is, once you get good at this, I'm writing out little baby steps. You can do a lot of these in your head if you know what you're doing, and that's fine. Here I would call this step, this is sort of gather the u's at the front, and then the x's after. I'm just trying to rearrange things. Usually they're going to be multiplied in there, so you can just rearrange them however you want. I'm going to rearrange stuff so that the u's are all together, and then everything else that's left over is next to it. And now is the step at which you will know if you chose correctly for the u, what am I going to do with this 2x dx? You look back up here and you hope that that equals the du, which it does. So this 2x dx right here is actually the du. All right? So here you plug in the du. And you might think I got lucky because that leftover piece just coincidentally happened to equal the du. And the answer is yes, I got lucky. That is necessary in order for this to work. And like I said, there are many, many examples where it just doesn't work. Now, I'm not going to ask you to do one that doesn't work on the test, but this is what can make the substitution difficult. All right. Anyway, the hard part is over. Now it says integral of u to the 6 du, and I can do this integral. This is actually a very simple integral at this point. It's written using the letter u rather than x, but you can just imagine, what if it said x here? It would be 1/7 u to the 7 plus c, right? So in this step, I do the antiderivative. All right. I hope we don't have a lot of, I know some people, just because I've been around, I know some people are like integral sign haters. Some people just don't like writing the integral sign. I would say it's a free country, but you should write the integral sign. I mean, you're going to be confused about what you're supposed to do at this point. To go from here to here, I did the integral in that step. If you are someone who just doesn't like to write the integral sign, you might forget to do that step. All right? Anyway, the work is basically done at this point. There's one final step, and that is because the original question was phrased in terms of an integral of x, I should give my answer using x as the variable. And so the very last step is to plug in, I'm going to say replace the x's. This whole problem, we began by saying u equals x squared plus 10, right? 10, yeah. Like so. And this is my truly final answer. All right. The last step is to plug the x's back in just based on what u is equal to in terms of x. All right. You are undoing the first step. All right. This is the u substitution. I don't know if this seems difficult. I don't mean to hype it up so much. That's how we do it though, in general. Anybody have a question as of now? I'm going to do one more. Actually, I'm going to do more than one more, but let's just try another one. Right? All right. Let's try another one. Let's try the integral of 3x squared square root x cubed plus 1 dx. All right. Because I have the square root and that stuff inside of the square root, this is much too complicated to just look at it as a simple power rule antiderivative of something. You might as well think of the square root sign as a 1/2 power, right? I mean, this is how we always think of the square root sign as a 1/2 power. But anyway, it still looks very complicated. There's no way to distribute that 3x squared into the 1/2 power. And so we should more or less right away decide you're going to need to do the substitution in this example. Anybody would like to suggest what we should pick the u to be? The general strategy, remember, is the u should be the inside of something or other. What do you think? X cubed plus 1, yes. All right. Let's just try and follow the same steps we did before. What comes next? We should determine the du. So the u is your choice, and hopefully you choose correctly. There is a right and a wrong answer, but you have to come up with the u yourself. The du, once you chose the u, the du is determined. That is the derivative of u. And can someone say, what's the du going to be?
3x squared.
3x squared dx. Great. Remember, the du always includes the dx. All right. Excellent. This is the choice of the u. So this one you choose. This one you figure out, right? This one is based on the first choice. You find All right. Anyway, the next step would be to try to plug in the u where it goes, and this is an easy step. This would say integral 3x squared u to the 1/2 dx. I just put u exactly where it goes on the inside of those parentheses. The next step, I have a little simplifying where I like to gather the u's at the beginning and push everything else off to the end so that it's all together. So I'm going to gather the u goes first on the front, and then everything else, which is 3x squared dx, goes at the end. And if you've done things properly, hopefully this stuff magically is the same as the du, and it is in this case. This is confirmation that I did indeed choose the u properly. So now it just says u to the 1/2 du, because that stuff over there happens to be equal to the du part. If it doesn't equal the du part, it means you probably chose the wrong piece to be the u, and you should start over and try with a different u. All right, let's just continue. What should we do from here? Now it just says integral of a power of u, and we should do the antiderivative. So here I'm going to do the antiderivative. By increasing the power by 1, the power is currently 1/2. We increase by 1, it becomes 3/2. So this becomes u to the 3/2, and then a 1/3/2, and then a plus c. That's the antiderivative. And there should be no integral sign at this point, although there should be integral signs before now, but not right now, because that's the step at which I actually did the integral. That's where the magic happens, as they say. And now we're pretty much done with the work of this problem. Just the very last step is to replace the original variable of x. So I'm going to plug the u back in, right? U is x cubed plus 1. So just write this again, but put x cubed plus 1 there. It'll say 1/3/2, which is 2/3 if you like. Not u. I'm putting x cubed plus 1 to the 3/2 plus c, like so. Yes?
Where did the 3x squared go?
The 3x squared, yeah, 3x squared dx is du. And so this turned into du.
Oh, so you're just writing du's.
Yes.
Okay.
Yes. Maybe your real question is, where did the du go when I did this? And that is, when you do the integral of something, the d whatever goes away. Like if it was something like, what's the integral of x dx? The answer is 1/2 x squared plus c. And you could ask me, where did the dx go? And I would say, you did the integral, so the dx goes away. So the du the du kind of disappears in this step. But it's because the du together with the integral sign indicate that you haven't done the integral yet, and once you do it, they both go away. All right. I have one for you all to try, but just before we do that, I would like to point out, you can always check your answer on these. Like I said, I think these are a little tricky, so if you have a few moments on the test, you might want to check your answer. Check it. The whole point of this problem was that the antiderivative of this is equal to this thing that we eventually got at the end. What that means, we could check the answer by taking the derivative of the last thing, and it should equal the thing that we started with. So you should be able to do the derivative of the answer. And if it's right, then you should end up with what you started with. So I'm going to do derivative of the answer, which was 1/3/2 x cubed plus 1 to the 3/2 plus c. Now if we do this derivative, 1/3/2 is a coefficient, so it stays 1/3/2. And then how do we handle the derivative of that? You would do the chain rule. And this is not a surprise because the whole substitution strategy is based on the chain rule. So you would do the chain rule. The 3/2 comes down to the front. So it's this times, same thing on the inside. Decrease the power by 1, the exponent becomes 1/2. And then I multiply times. Derivative of the inside is 3x squared. That's the derivative. The plus c goes away because the derivative of a constant is 0. And then these 1/3/2 cancels 3/2, And what remains is x cubed plus 1 to the 1/2 times 3x squared. And that really is the same as what we started with at the very beginning of the problem, right? This is the same as the beginning. And that means that it's correct. So this is how you would check your answer. And you can always do this in a problem like that. All right. Anyway, I got one for you all to try. How about integral of 12x times 4 plus 6x squared to the power of 5? See how it goes.
Because like I'm trying to process
I'll go with you if you want.
Oh.
Yes, this is great. Now you should do the integrative. So this is just you should like
Oh, okay. That's so like.
replace the x. Alright.
Yeah, that's great. Yep.
It's 1/6 to the 6. Yep.
Oh, wait.
Mhm. Yes. Excellent.
Hey, what do you got?
I got 1/6 times.
I don't know.
Six x squared.
Okay.
To the 6.
you.
Plus C.
Okay.
You know the X bracket at the very end, like do you have an X bracket?
Yeah. Yeah.
All right, let's do this one. I got one more to do before we go today. Actually, slightly bad news. Every one of these has been an easy one, unfortunately. Although there's one extra thing that you have to do most of the time, but it's not such a big deal. Anyway, everybody correctly identified the u should be the inside of the parentheses, which is 4 plus 6x squared. And then the du is the derivative of that. It's 12x dx. All right, and now I start to try to substitute stuff into the integral. I hope you can see why this is called the substitution trick. All right, so here I plug the u in. Now if I rearrange things, I like to write the u's first and then everything else afterwards. So what's left over is 12x dx. And fortunately, 12x dx happens to equal the du. And so this is integral u to the 5 du. And then you actually do the antiderivative here by doing the power rule. So this is a fifth power. We should increase the power by 1 and then divide by that number in the front. So this becomes 1/6 u to the 6 plus c. At that point, the integral sign should go away because that's the step in which I did the antiderivative. And the plus c should appear. All right, and then just the very last step is to plug the x's back in. So my final answer is 1/6 4 plus 6x squared to the 6 plus c. There you go. It looked like people worked that out for the most part as I was going around. Anybody got questions about that? All right, so like I said, these have all been kind of easy ones. There is usually one other step that we have to do. Usually we need with 3 E's. One more trick. It's very simple. So I hope everybody's feeling good about that one that we just did. This is the trick which I call divide the constant. You'll see what I mean. Divide the constant, all right? Here's just another example. How about integral x 7x squared minus 1 to the negative 3 power dx. All right. So it has a similar kind of structure to the one that we just did. We should choose the u to be the inside of the parentheses. So it's going to be 7x squared minus 1. And then the du is the derivative of that. It is 14x dx. Remember, you always include the dx in the du. Du is just the derivative of u. And right here, I am going to do the divide the constant trick. It's not really much of a trick, but it's right here. This 14, I am going to divide to the other side and write this like 1/14 du equals x dx. This is what I call dividing the constant. Why do that? You'll see why. All right. But this is the old divide the constant trick. Okay, anyway, let's just proceed. Everything now will go just like it always did in the other examples. So I'm going to begin by putting u where it goes. So I have the x in the front and then u to the minus 3 dx. Right? I am just sticking u in the parentheses there where it goes. And now I'm going to gather the u's at the beginning, and then the rest of it is x dx, all right? And here you can see why it was necessary to divide the constant. X times dx is right there. This equals 1/14 du. It does not equal du. In all the other examples we did, that part actually equaled du on the nose, but usually it doesn't. Usually you have to divide by a constant to make it match up. So this is integral u to the minus 3 times 1/14 du. That's the extra little seasoning in the dish. is the dividing the constant. You get this extra 1/14th, all right? And how do we handle the 1/14th? The next step would be to do the antiderivative. What happens to this 1/14th? This is actually a coefficient. I mean, it doesn't really look like it because I wrote it last, but it is just this thing times this constant. And so it should be treated like a coefficient, which is to say, I think the simplest way to handle it is a constant coefficient can just factor all the way out of the integral. It just ends up being a coefficient in front of the answer. And so I get 1/14th in the front. And now we can continue as before. Do the antiderivative of u to the minus 3. That is, we increase the power by 1. Minus 3 becomes minus 2. So this is 1 over 14, and then 1 over minus 2 u to the minus 2 plus c. That's the integration or the antiderivative step. And then last step, you replace the x's, and that's it. So here we get those constants. If you like, you can multiply them together. I don't care. 1 over 14 times 1 over minus 2. And then u to the minus 2 becomes 7x squared minus 1 to the minus 2 plus c, like that. This is how we do it. Can you all try one of those? We got 8 minutes left. I think that's plenty of time. How about integral of x squared 7 plus 2x cubed to the 4. All right. This is very similar to that one. Maybe I'll try and scroll them all. You see everything? Okay.
Do you mean also divide the x?
No, we weren't sure.
So typically I only divide the constant like this.
Right.
So if you wanted to, you could divide the x squared also, then all this stuff. It's not wrong to divide the x squared also. Yeah, so it looks like you're doing the right
Like what is u exactly? It's helpful to write that out. Yeah, so I would this step I would just move the so and then what is x equal to
All right, I think I better do this one just because we got to leave in a few minutes. It is very similar to the previous one, and I saw people seem to be getting started well, at least. So I should choose the u to be the inside, as always, 7 plus 2x cubed. And then the du is going to be 6x squared dx, all right? And I'm going to divide the constant, which is the 6 in this case. 1/6 du equals x squared dx, all right? And now we should start doing our substitution. So first I plug the u in where it goes. It just x squared times u to the 4 dx. Do a little rearranging here. U to the 4 is the u part, and then what's left over is x squared dx. And x squared dx equals 1/6 du. And so this x squared dx turns into 1/6 du. So this looks like integral u to the 4 times 1/6 du. All right. Now I have an extra constant on the inside of the integral. That can always just pull all the way out. So this says 1/6 integral u to the 4 du. And now we are ready to do the antiderivative. U to the 4 becomes 1/5 u to the 5. So this looks like 1/6 times 1/5 u to the 5 plus c. And then we replace the original variable, which is x. You can see at the top there, u is 7 plus 2x cubed, so this becomes 1/6 times 1/5 times 7 plus 2x cubed to the 5 plus c. There you go. I saw a lot of people wrote 1/30. That's totally fine too. All right, that'll do. See you all next time. Please let me know if you want to do some of them problems in my office. I would be happy to do it.